Um, Good evening, everyone. My name is Otimong Jonathan. I'm a year two student at Makerere University, and I offer software engineering, and I'm in year two. Welcome back to my YouTube channel. As you all know, we have already been discussing about AI development. So, this time round, I want to take you through a specialized presentation. According to our group, we are doing knowledge graph based reasoning for forecasting input costs and capital adequacy in smallholder farming. We shall have to go through this small contents: the introduction through related work, then the problem statements, the research questions and the objectives, and then research contributions, and then we shall finish up from there. The background and the introduction. Smallholder farmers operate in high risk environments of financial uncertainty in pre-planting periods. This basically means that farmers face high risks when they are planting. For example, they can't decide what to plant. They don't know if their initial investment income is enough for this and that. What this model will do, the model will help farmers make choices when they are planting. The introduction, while many existing AIs mainly focus on predicting yields, this one is mainly focusing on predicting the initial input. So we are not focusing on output, but we are focusing on what? On input. Our solution, a proactive, we shall develop a proactive AI that uh, helps us aggregate pre what? Uh, it will help us aggregate predicted costs of inputs and then collectively give us a total what? Aggregated total input cost. So the key concepts through our what? Our um, our model are agricultural investment estimation, input cost forecasting. This mainly deals with predicting future market prices of agricultural inputs. Then knowledge graph driven decision support, a structured database that it involves a structured database that encodes relationships and rules. So that this is the brain of the system. This is what will help establish the relationship between different features, which are called nodes, and then the edges, which are the relationships between the features. Then capital adequacy, uh, available capital against the projected expenses. So, what's the available capital? The available capital is the money at hand. Then the projected expenses are the predicted total cost input that the AI will predict. Then risk-aware farming tools. So uh, risk-aware farming tools mainly deal with tools that help us establish what risks and what and it will help us establish risks involved in farming and then help us what overcome such risks. So the related works, as we talked about, people who have already developed similar AIs. There is Zhang et al., there is Li et al., and then Ruan et al. Those are the people who have done this before, but we shall also be doing a similar approach while borrowing some knowledge from such people. So, the problem statement. So, the domain application problem. Many smallholder farmers in Uganda face a problem of risks, high risks, and they depend on estimates to focus on what? Or to predict like their initial investment cost. So they estimate, but they don't have real knowledge and real data about the actual estimates, whether they are actually true or false. So what will our AI do? This is where the computational problem is. This in the real world, forecast the AI will forecast multivariate volatile prices, representing agricultural knowledge in a machine readable format, and then turning raw data into personalized actionable insights. So our system tackles this using a hybrid approach, which involves a time series and a deep learning model, which mainly we shall use our knowledge graphs to do this. So we shall now proceed to our research questions and objectives. So the research questions are: what AI models do to accurately uh, forecast agricultural input costs in smallholder farming? Then what designs the knowledge graphs give to represent relationships between crops, inputs, and environmental factors for reasoning. Then, what hybrid modeling approach best predicts total investment inputs, total investment requirements? Then, what recommendations are given to smallholder farmers after system evaluation on capital adequacy? So we shall also have some objectives that our AI is going to meet. So it will develop a hybrid model integrating time series and knowledge graph based reasoning for accurate input cost prediction. So the model is going to be a hybrid whereby it takes in more than two model architectures to come up with what? With desired output. Then to construct an agricultural knowledge graph, encoding, which encodes semantics between different features of the what of the data. For example, the relationships between crops and their input costs, the relationships between districts, crops, and regions. Then to also build a capital adequacy reasoning module to assess farmer investment capacity. So this will help invest to check the farmer's capacity using the projected expenses versus the capital at hand. Then to also implement a mobile first decision support system to deliver results to end users in real time. So we shall now proceed to the next slide. So research contributions and outputs. So we developed a hybrid AI forecasting engine that integrates a time series model and a knowledge-based graph model to predict agricultural input prices with improved accuracy. So we also built an agricultural knowledge graph that semantically links crops and other features. For example, the inputs desired in a selected crop, the regions where such a crop can actually be more be more invested in with low input costs. Then also for example, uh, that semantic link or the relationship between regions and districts. And then we also designed a capital adequacy reasoning module that evaluates farmers' budget against projected costs, recommending alternatives. And then we developed a mobile first edge compatible decision support system with offline accessibility among rural smallholder farmers. So the methodology mainly, our methodology architecture uh, mainly involves around four steps. It has the input what section or the layer whereby the user inputs data into the system. Then it has the brain element that helps to establish the relationship between the encoded the encoded input data, and then it has a knowledge base that will help us reason out how contextual factors will affect the final total investment input. And then it also has the output layer that will give us the final output. So we shall also move to model architecture and mathematical foundations. So we mainly focused on graph attention network and residual robust neural network. So the reason why we focused on this is because of their development process. They have like their hybrid models, and they have multi layers that can easily capture even hidden features and hidden relationships among data features, the nodes and the edges. So uh, this is a graph attention network, that is its architecture and how data flows through the architecture and how it's evaluated and processed into what into the output we desire. So the graph attention network mainly focuses on establishing the relationships between the different crops, the different features, for example, region, the time, then the districts, the crops, the inputs. So it establishes those features as nodes, and then establishes the relationships between those features, and that is done using edges. So we shall now go to the math. These are the mathematical equations involved in graph attention network, and then there's also robust residual neural network. So robust residual neural network is mainly it's a neural network that captures and helps us forecast the actual prices using the relationships established by what by the graph attention network. So as I mentioned earlier, this is going to be a hybrid model, meaning that it's going to uh, combine more than one model and therefore give us what final desired output. So we shall go on to the next slide. These other slides show the equations that are involved in the um, the robust residual neural network, which is also called TAB network MLP. So these are the equations that are involved there. Um, it has mainly two blocks. There is block one, there is block two. So these are concatenated into one in order to what? To make the model more accurate and have a higher precision. Then this there's also block three here. There's a continuation of block three there. Then I will now take you through there's knowledge graph neural network. There's knowledge graph neural network conceptual flow and mathematical foundations. So those are the mathematical foundations involved in that model. So, and these are also its other equations. So now I'll take you through the dataset description and exploratory data analysis. So how did we generate our dataset? We mainly generated our data from two government organizations, that is UBOS and FAO, and then we combine the data into one in order to capture the relevant data columns that we require. For example, the seed price per kilogram, fertilizer price per kilogram, herbicide price per liter, pesticide price per liter, labor cost per day, rainfall index, soil fertility. Those ones are conceptual factors. So this will help us uh, come up with our total aggregated cost that we actually require as our final output. So this data set mainly had 16 columns, but we had to drop around 2 columns in order to remain with the ones that are applied to our data, our required output. So the exploratory data analysis is here. So this dataset spanned around 4 key regions with 12 crops and over 20 districts. So this dataset had 5 financial features that helped contribute to our final aggregated cost, but it also had some features that contributed to our conceptual factors. For example, the rainfall index uh, column, then there is also soil fertility index column. So these are the performance metrics, as we all know. R squared score, there is MAE, there is RMSE, and then inference time. So this contributes to the model choosing, like how you can choose your model. The better the metrics, that's the model you will consider. So these are the outputs of the different of the what of the exploratory data analysis. Then there is this. Then I'll now take you through model selection and deployment. So we mainly chose knowledge graph basing on what our description means. So knowledge graphs we chose GAT, and then a residual robust neural network because of their high performance accuracy and their perfect performance metrics. So to summarize, I'll talk about the limitations. The limitations are mainly the overfitting, underfitting, and what have you. So I would like to thank you for watching this video, and I encourage you to come back and watch more. Thank you.